Industrial pollution, particularly from carbon dioxide emissions, is a major contributor to climate change and environmental degradation. Power plants, especially the coal-fired plants, are the largest industrial sources of CO2 emissions. Manufacturing and heavy industries such as steel, cement, and chemical production release significant amounts of CO2 through combustion and chemical processes. Oil and gas industries extract, refine, and process petroleum products, generating high levels of CO2. Exploring the innovation journey, starting with 1990 to 2010, we saw the Sleipner project in Norway, the first commercial carbon capture and storage project, also known as CCS. During this period, the IPCC recognized CCS as a key climate solution. 2020 to 2030, the Orca DAC plant, the world's first large-scale direct air capture facility, became operational. 2030 to 2040, looking ahead, the focus is going to be on reducing costs, achieving global scalability, and aligning with net zero targets. By 2040, we expect to reach maturity in CCS. UN's goal is to drop the global temperature by at least 1.5 degrees Celsius by 2050. Greenhouse gas emissions need to be reduced by almost half by 2030 and reach net zero by 2050. Carbon capture works by trapping carbon dioxide emissions from industrial processes before they enter the atmosphere, reducing their impact on climate change. The process typically involves three main steps: capture, transport, and storage. Once captured, the CO2 is compressed and transported, often via pipelines to a storage site. It is then injected approximately 800 meters deep underground into geological formations.
Despite huge technological advancement in other fields, the big question is, do we have enough technology to remove CO2 from the atmosphere? The four major techniques used for removing carbon from the atmosphere are direct source carbon capture, direct air carbon capture, bioenergy carbon capture, and chemical welding. However, in this video, we will only be discussing the first three. Direct air carbon capture involves passing atmospheric air through special chambers. So this special chamber is heated to about 100 degrees centigrade, where the captured carbon is then dissolved, mixed with water, and then forcefully injected into rocks. Volcanic eruption activities lead to the chemical reaction of iron, magnesium, and calcium, resulting in basalt, which is a porous rock. The infusion of the CO2 into the basalt changes this to this. The next method is bioenergy in carbon capture. This basically takes cognizance of the fact that plants store their captured carbon in their tissues, thereby making plants our natural method for capturing carbon from the atmosphere. The compressed plant tissues are compressed and put in a furnace where it is used to generate power and other byproducts. The captured carbon is then injected into rocks as already discussed.
The oil companies choose carbon capture, utilization, and storage technology because it makes their business viable. The oil companies are ignoring the renewable sources of energy as it counters their core business.
Captured CO2 can be refined and used in medical use, food and carbonated drinks, and synthetic and fuel production.
It will take technological improvements, engineering solutions, and intentional efforts so that by the end of the decade, the cost of capturing CO2 can be further reduced from $1,000 per ton to about $300 per ton. Carbon capture utilization technologies will be among the many approaches that will reverse the damage and start the climate healing process.